Tom et al. Is going to be talking about A Tale of Two Maria. The best of times and the worst of times, distinguishing lunar volcanic history with crater density analysis.
Yes, indeed.
So despite better judgment, wait, I'm going to go down.
Sometimes if you're you have to just
Okay. Zoom basics. So let's get into the introduction here. So yeah, despite recommendations, we are going to talk about a large crater database today. So this goes to fundamentals, understanding the emplacement history, location, ages of our basalt flows, help us to understand the thermal history of the moon. That's very important. So, of course, over the last maybe 60 years, multiple approaches have been developed to determine the absolute model age of Mare surfaces. And typically these involve manual crater counting and measurements to identify the location and size of each crater, and then crank through the formulas on that. So the count area that's defined in most studies, it may or may not include multiple flows. Ideally, we want to, if we want to understand the age of a flow, count a single flow. It's quite difficult to determine that. Should note that past studies have identified erasure of small craters, which might be a younger flow obscuring a previous flow. So that becomes important later. That appears as an inflection on the CSFD plot. So the background for the study. So yeah, we're looking at a wide area, and we're looking at a lot of craters. So at this point, the manual methods become a little bit impractical. So, the preference is to engage an automatic detection framework. This framework employs crater detection algorithms, CDAs, involving a convolutional neural network, as some of that Stuart described earlier, along with deep learning algorithms. So, believe it or not, crater detection algorithms have undergone substantial improvement and refinement over generations. So they are getting better, question mark. But there are limitations, and I think especially this group is quite cognizant of that. A lot of these studies come from not the crater counting community, but they originate in computer science departments, maybe in database labs. So there's a general lack of understanding of the crater morphology, morphometry, etc., which can be a hindrance. Some of the problems we run into are unrecognized craters. Sometimes they can include positive relief features. Secondary craters are always something to deal with, of course, and they do plague these large databases. So all of these things affect the AMAs, the absolute model ages. So for that reason, we kind of back off a little bit. And in this study, we look more at relative ages and try to de-emphasize the AMAs. So our objectives are fivefold here. If possible, with this data set, count areas, determine whether count areas with disparate absolute model ages can be distinguished. Find areas with uniform crater density. That's useful if you're defining a count area. You can kind of map it as uniform. Identify single or multiple lava flows as via variations in crater density. And then lastly, we'll look at variations in impact relationships. And craters on disparate terrains. Which is basically the Mare surface versus a Mare edifice. So the data, do want to keep an eye on the time. I do really hope to have time for questions. And a little bit of debate at the end.
I can warn you at 5 and 10 minutes if you'd like.
Okay, sure. I've got the clock up here as well. So data, we're using LROC, WAC-NAC, morning and evening, Kaguya, the train camera data. Mare age units, reference 19 years, Hiesinger et al., 2011, and all the predecessors. The crater detection algorithm is a slew of references here that mainly came out of a big computer lab in Perth, Australia. Working with those folks there, they were using yellow version 5 at the time. I think that's been updated a few iterations.
Yes.
And based on that crater detection algorithm, it was applied to the moon. This is all about the moon. With 234 million detections between plus and minus 60. And this is craters 70 meters and up. So our initial study, we've got to pare that down a little bit. Over 200 million craters, a lot to deal with. So we're just talking about Oceanus Procellarum in the west. Craters down to 70 meters. And that so it boils down to about 320,000 craters. This is probably a vital note. Secondary craters are not removed in this data set. They did remove secondaries kind of with a clustering mechanism above 300 meters. But it's just not realistic at these smaller crater levels. Continuing the dating methods. So to produce the point density cloud, we used ArcGIS 3.4 and then output to the 3x3 kilometer grid cell, raster cell. That's taken from an area of 15 kilometers square. And then we kind of layer cake, slice it up into layers of 50 meters in diameter crater sizes. So you're working with these different layers. It makes the data more manageable that way. So the end result, the data is a continuous raster surface where each cell represents the concentration of points or AKA craters per unit area of a given size. So just a little bit of history here. We kind of started with a grid cell approach. You can see the middle diagram where we're kind of overlying grids. I didn't find that that effective, and then I found a study that actually Lillian and Mark Robinson worked on. I think it was 2014, where they did an aerial crater density bit of work in northern Mare Imbrium. So that was a bit of inspiration. Thank you, Lillian. So if you're going to go hunting for lava flows in data, probably good to define the criteria by which you're evaluating your data. So this is kind of a work in progress. Every time I look at it, I do tweaks to the overall criteria. But I think generally we just want to say, and I should have a diagram. My apologies. I'm glad I'm not being graded. But if we have an existing flow, you know, it's been there exposed to space and cratering for a while, it's going to be dense. If we get a new flow, if it's a thick flow, it will obscure that existing flow and kind of reset the crater and clock. So we'll have both lower density and smaller craters. If you have a thin flow, I've showed that at the bottom, you know, it gets a little bit more complex because some of the larger craters still exist. The thick flow over an existing Mare is probably the easiest to pursue in the data. Anyway, you can see this is kind of going on into the crater density analysis, but then also at the end, add some of the obvious ways to detect a flow, going back to Shaver 73, you can see a flow boundary. That's kind of nice, but pretty rare. So morphology can tell the story. You know, I'm a big user of geochemistry, so that's another way to detect lava flows. You know, but the moon can be a conspiratorial body, so sometimes you might get a later flow with the same geochemistry, and it doesn't really help you distinguish between them. So let's look at some of the data here. So this is the study area in northern Oceanus Procellarum. And the purple dots do include, this is one layer. I mentioned the layer cake. So the layer cake, the layers are listed in the lower left on this slide. So what we're looking at here is only craters of size 500 meters to 550 meters. It just gets silly and overdense if you had probably 3 or more layers at a lower diameter size. So let's run those layers through our density process. And we've got some of the screenshots from the tool from ArcGIS in here, but mainly we'll focus on the results. So again, looking at all of northern Oceanus Procellarum, I have highlighted basically three different Mare boundaries from Giguere et al. 2011, featuring area P10 on the upper left, and then P50 on the lower right of each slide. These slides here, I'm going to show the 4 slides are 4 slices of the layer cake. So I'm going through different densities. What I want you to notice is if we look at P10 on the left side, this is craters 70 to 100 meters. It's rather sparse. Of course, the darker purple is more dense, higher density of craters. Now, if we look down to the lower right on that same left slide, we see that P58 is quite dense, with craters 70 to 100 meters. So there's quite a contrast between the 2 areas. I think that passes 2 of our initial tests about being able to identify areas of disparate density and also uniform density. If we move to the right slide and change the slice of the layer cake to 150 to 200 meter diameter craters, we're seeing actually the P10 has a few less craters, and actually P50 is has a lower density of craters. Now let's go up in size here even more. Left side is 250 to 300. I think we're actually gaining the density of craters in P10 and reducing the number of craters in P58. So ultimately we get to kind of jump up the cake to craters greater than 1 kilometer. This is in the note. I point out that this is kind of the size that the typical crater counts of the past, due to the remote sensing data available, would count in this range 1 kilometer and above. I think Harry Hiesinger did use that number quite a bit to make the moon manageable. But take a look at P58 here. It's just devoid of 1 kilometer craters. So we know that that previous study is going to get a young age for that area based on that. And sure enough, we can see in the corner of P58, the age designated is 1.33 billion years, whereas P10 is around 3.3 billion years. So crater density is really telling us a story here. And I probably should have put them on the same slide, but if we go to this left slide, I went backwards to P58. So a young Mare surface is going to have a high density of small craters. Sure enough, it does. P10 has been well worked. Craters have reached the saturation point at that small size. So it's quite devoid of craters.
Question.
Yes,
So if it's been worked and it's saturated, then shouldn't it have the same number of small craters? And isn't the fact that it doesn't a concern about the detection?
that could go to I mean, they would be more degraded, even though they're still present. So that would go to the ability of the database to pick up those craters, identify those craters, I would think.
That's what I was thinking in my head. Another thing I was thinking was perhaps on the 1 kilometer one that you have up here now, you said that there aren't secondary, well, no, you said the secondary should be removed from this, but I mean, maybe my brain is drawing lines. It looks like there are lines of enhanced crater spatial density that might be secondaries, but again, you said that they were removed, so.
Did I
I'm a
say
little
that?
confused about the splash.
No.
You did.
Yeah, they're actually here, so thank you.
Oh, I thought you said that they weren't removed from smaller, but they were from larger.
Ah, good point, good point. This database is kind of divided into two sets. 300 meter and up. Secondaries removed. But for consistency, I use the 70 meter and higher.
Okay.
And none of the layers have secondaries removed.
Okay.
For comparison purposes. So, Dr. Lowell, you are seeing lines out of those shapes.
Well.
And it's very appropriate on this, in this environment.
Better get back to the telescope. I might find nails on Mars. I'm gonna apologize for my phone keeping ringing. Apparently, I'm on some mailing list in Michigan. Turn on do not disturb.
So good observation, and that's why, yes, it's good to know our data, and with these big databases, we have to be especially careful. So, okay, so using that philosophy, keeping an eye on the time here. If we then do a ratio. But then in this case, sorry, I'm just showing 70 to 100 meters. But I previously did a ratio offline. And these areas that have high density in the small crater population and low density in the large crater are potential areas for searching out flows. So I've got a side LROC WAC image here. This might be at the NAC level with an area that's kind of basically devoid of craters. So these are potential areas to seek out and look at in more detail. Okay, so that's one scenario we can do with a large database. Here's another one, just moving around the data. Look at the center diagram. We notice that around some of the craters, there are zones of exclusion of craters. So around the 6 kilometer crater, we have a lower density of 300 meter craters. Then moving to the right, we see a lower density of 70 meter craters around this crater as well. So that just fosters playtime in a way. And we did another analysis where we had parsed the data in a different way. And our goals were to check to see if the density of 300 meter craters affected the smaller craters in the vicinity of those 300 meter craters. We also investigated whether the terrain has an effect on crater density. And then what is the density of small craters based on the previous Maury age units that we looked at? So in the center diagram, we've got all the 300-meter craters listed kind of around P58. If we map all the craters in the lower right, we see around Malm's Hing, all the craters down to 70 meters, and then the purple dots represent 300-meter craters. So let's take it even another step further. What's the density of 1 to 150-meter craters around 300-meter craters? So we've got two zones around this example crater here at 1 crater diameter and 2 crater diameters. You can see on the left diagram how we've mapped 3 150-meter craters within 1 diameter and about 10 or 12 150-meter craters in the within 2 diameters. So that's one example. Move to the right around Malm's Hing, and we see the result of that with the more craters surrounding that edifice. You can then extrapolate that to the regional level and look at, looks like my figure shifted, but Mons Runker E, 6.8 kilometers diameter, upper right, has a distribution of 300-meter craters around it. Each of those is 1 diameter, 2 diameter, and they're color coded by the number of craters in each zone. So you can, I probably should have pulled out a little bit more in this diagram. You can see that generally the 300-meter craters around Rumker E have either more degraded or less 150-meter craters in that vicinity, probably due to ejecta coverage from that crater. Moving to the center lower diagram, Mons Rumker. This is a Maury edifice, Maury material. And sure enough, we see that the 300-meter craters tend to be yellowish in color, which means a lower density of 150-meter craters. 6 minutes. Okay, thank you. We're in trouble. Okay, but zooming along, if we take that out to the regional level, we kind of did the same analysis, 300-meter to surrounding 150-meter craters by spectral unit in Hiesinger's data. And they're color coded so that you can see them sort of plainly, small. And the results show that statistically, it's pretty flat if you're going from young Maury units to older Maury units. There's a slight, of course, we overinterpret the data. There's a slight downward trend, which might mean that on older Maury units, there's more degradation. So this either a lower density of 150-meter craters or a lower recognition with master database. Okay, so these are examples of using that ACD and also a large database. So come up with other uses of this type of data. Basically, we just covered 2 simple examples, crater ejecta and maybe a relative age comparison. And I think this is a good list to start from, but I would love to hear about more ideas of how to use, massive amounts of craters to do studies. So let's just highlight a few of these. You can look at terrain, steep versus flat terrain, because we know the slope has an effect on crater retention. Maury versus highlands. pyroclastic deposits. I think this could be a tool for identifying pyroclastics. Sometimes they're not easily seen, especially pyroclastics on Mare. Thin versus thick regolith, mass wasting events, and maybe self-secondaries. So that's an initial list. So our findings are, maybe we don't restate all these, but in the interest of time. But you can see that we did find a difference when using this massive amount of craters that wasn't highly dependent on AMAs for an answer. When we're looking at terrain problems, degradation problems, slope problems, AMA is not always required. So I wanted to get to this slide. So the future of automated crater databases. We've heard good and bad of them. So discussion topics. So this trend has popped up. These large databases have appeared. Are they gonna just kind of fade away? Is this just a temporary phenomenon? Or are they gonna keep proliferating? Are these databases gonna regress, stay the same, or are people working on improvements? I guess I would argue that they probably will proliferate and people will attempt to make the improvements over time. So trends, databases increasing, and so the general trends are they're finding more and more craters. I mean, 230 million craters is kind of insane. They're increasing the breadth, the spatial extents of these databases. And they're getting to smaller and smaller crater diameters. So just my general suggestion is, can we embrace this technology in some manner? Try to examine approaches to take advantage of technology. I think we'll just leave it there. Maybe leave it on this slide.
Thank you, Tom, and all. In lieu of any questions online at the moment, I'm going to make a comment. If you could go back to slide 17. So I'm going to express a skeptical standpoint. One minute, that one. Nope.
This one?
Nope. One more forward.
No, other direction. There.
That one.
Okay.
Yes.
Did I show too much detail here?
So too far, and I can see it.
His eagle eyes.
Remember, this is just 150 meter craters.
Yes, but so you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 craters here. But this crater, this crater, this crater, those, and I would even say that's a crater, are in your size range but aren't identified, which would be another 25% or so. And so this gets to the question that I posed earlier of, is degradation, I mean, I would actually not even say these are that degraded. These are pretty visible to a human eye. So the question of, can we use these? Should we use these? Are they good enough for what we're trying to do? And I might argue that using this for an analysis like this, when it has, I would argue it's missing stuff, is that good enough for what you want to do? If you're trying to show trends or stuff.
But aren't those craters, that looks like 155 to me.
I guess it gets to the question earlier of how much validation was actually done with this, and should we perhaps think about what as a crater community we would want in order to validate some of these databases. So for example, when you train these models, you have a training data set and then you train. Should you hold some of those out and have an independent check on those? And a lot of people don't, but I think that you should. And I've now pontificated on a question for longer than the time slot. So I'm going to slowly go back to my chair, and if anyone else has questions as I walk, feel free to ask.
Jamie has 6 questions, so.
Oh,
All right, that's a dinner time thing or a discussion at the
Can I
end.
make a quick comment? I really like this idea of using crater density as a proxy for like figuring out these other geologic units, so we should talk more later.
Yeah.
To not delay the next talk, but I think that's a
I see a lot of potential and then kind of got into the cumbersome details of cranking it out, but it's like,
It
where do
could,
you stop?
it could also bypass the differences in ages that we have between different groups and stuff. You just talk about the N1, right?
Yeah.
And so it would skip all the other problems.
Mhm.